You'll notice that a lot of different kinds of medications do have chlorine in them. You'll see that Cl group. So for example, you might be familiar with Wellbutrin here. This is a type of an antidepressant that a lot of people use right now that are taking antidepressants. It's on the market. Very popular in terms of your choices right now as an option as an antidepressant. Also, Lunesta, this was very big in an ad campaign at least last year. I'm not sure if it still is with the little butterfly. This is the structure of Lunesta, and you see the Cl in it as well. I just wanted to point out that although you see these chlorine atoms in these drugs, what you almost never see is an acid chloride. In fact, I don't think I've ever seen an acid chloride in a final pharmaceutical product or a drug that we take. And the reason is because they're so reactive that you wouldn't want to have that in something you digest. So just keep in mind when you do see the chlorine in these drugs, it's very different from the acid chloride. So for example, Wellbutrin, it is very unlikely that it would have thionyl chloride in order to make it. And if thionyl chloride was used at some point in the synthesis, it was not to put that chlorine atom on, it was to put something else on. But in terms of drugs that don't look like maybe this compound was used in the synthesis, many of them might have used thionyl chloride because it's such a reactive, it generates such a nice reactive intermediate that you can go on and make a bunch of different compounds from that intermediate. All right, so let's think about how to draw the Lewis structure for thionyl chloride. Oh, actually, let me let you tell me how we should start this Lewis structure. So which atom would you expect to be in the center of a Lewis structure for thionyl chloride? All right, let's take 10 seconds on that. Looks like we have some fast thinking here. A lot of last-minute answers coming in. Okay, we have a split decision. So, you know what, actually, let's think about this for a second. So hopefully it was a time issue in terms of looking at the periodic table, because let's have you tell me what are we looking for here? Yeah, okay, we're looking for the lowest ionization energy. So this one can be tricky because oxygen looks like it's in the middle because of the way it's written, but we need to start by looking at the lowest ionization energy. So if we look on the periodic table, comparing, for example, S to O, if we have S, it's below O, what happens to ionization energy as we go down a table? It decreases. If you're still not completely up on the periodic trends, that is stuff that's going to be on the first exam, so make sure that you're able to do this without taking too much time to think about it. We would expect the ionization energy to decrease. That means that sulfur has our lowest ionization energy.